Okay, welcome to lecture. We'll get started in just a second or two. Give everybody a chance to get in. We'll be continuing on with where we left off, which is chapter 14. Again, we'll be continuing on with chapter 14 here. We finished talking about salts and everything, I think, last time. Again, as always, if you do have a question, feel free to ask it there in the chat box. And again, even if I moved on, I will come back and get to your question. Okay, so we're going to continue on here in chapter 14 for a little bit. Then we will stop, and as hopefully you know, the exam will happen at about 11:30 there, our normal kind of lab time. It'll be available for you to start taking, and you could just do that, obviously, during that lab window block and take your exam. And then obviously we will pick back up on Thursday and continue lecturing. So we're just going to keep lecturing to kind of keep on pace with everything. So the next thing we're going to talk about then is oxides. And oxides are basically metals, non-metals that have oxygen in them. And these guys here, there are certain types of oxides that when they react with water, for example, they turn basic, they turn acidic, or they could be amphoteric. So on the left-hand side, what we got going is our guys over here that are typically where you'll find our basic, except for a couple over here that are basic as well. These are our basic oxides. So if you think about it, we got sodium oxide, potassium oxide. And again, when these react with water, these are really where a lot of our strong bases come from, right? So the first two groups on the periodic table are essentially your basic oxides, again, with a couple over here on the right-hand side, also part of that. Typically, when we get our nonmetals that have oxygen in it, or our nonmetal oxides, these are typically our acidic oxides. And they're acidic, for example, if you take something like CO2, if you take CO2 plus some water, that's going to get you carbonic acid. So a lot of these are nonmetals that contain oxygen is really where a lot of sort of our acids are derived from when it does react with water. And then we do have some amphoteric guys. And a reminder, amphoteric means it could either be an acid or a base, right? So it can act as an acid or a base. And again, it could kind of go either way. So there's a few of those sort of littered over here, over here on the right as our left-hand side as well. So these oxides, again, when they typically will react with water, for example, will either make perhaps a base, make an acid, could do a base or an acid if it's amphoteric in that substance. Now, so we've been talking about some definitions of acid and bases in this chapter. We talked about the Arrhenius definition, which is essentially something that produces H plus or OH minus. Talked about the Bronsted-Lowry definition, which is our proton acceptor and proton donor. So there is a sort of a third definition of an acid and base, and that's one that was brought out by Lewis. And when we think about Lewis, right, we think about Lewis structures. And when we think about Lewis structures, we think about electrons. So Lewis acid and bases deal with a definition of an acid and base that actually deals with electrons, which is kind of an easy way to remember that, since that's usually what we think about when we think about Lewis. So he said a Lewis acid, get these up here. Oops, come back. So a Lewis acid is a electron acceptor. Write that in for you. And a Lewis base is actually an electron donor. So it donates a pair of electrons. So talking about barely a pair of electrons in this case. So in this case, what we got going on here is our H plus is electron deficient, right? In order to become positively charged, you got to lose some electrons. So you're missing some electrons. So the OH minus here will donate its pair of electrons over, and we make water. And again, this would then be our Lewis base, and our H plus would be our Lewis acid. As you can see, it's still the same definition, sort of as Bronsted-Lowry. Our H plus is really being donated to OH minus, so that's our acid, and the OH minus would be our base. Here, same thing. We have our deficient H plus. Our NH3 has those pair of electrons that, again, it could donate over to our H plus, making our H plus, again, our acid, our NH3 here, our base. Now, remember that in terms of Lewis structures and all that good stuff and electrons, just because something has electrons doesn't necessarily mean it could donate it. So usually when we're talking about sort of electrons, usually there's some type of polar aspect of it, some unequal sharing happening there on these unpaired electrons, and that usually allows them to be sort of donated in the sense of a Lewis base. So again, just because you see electrons doesn't necessarily mean that it has the ability to sort of donate them. So those are important aspects to keep in mind. Now, when we look at this here, oops, come back. When we look at this here, again, if we look at this is boron trifluoride. It's an incomplete octet. You may remember, incomplete octet means that it is essentially electron deficient. And again, here we have our polar NH3, right, which is going to allow really those electrons to be donated over to our deficient boron. And here we end up with a bond between the two. This is also a nice demonstration that a Lewis acid and base can be used for that definition of acid and base without any H plus being transferred. So in the other two examples that we looked at, although we sort of looked at them in the sense of, just look at them real quick, although we looked at them in the sense of Lewis acid and bases, we could have still looked at them in the Bronsted-Lowry definition, as there was an H plus that was still being sort of transferred and accepted. But here in this example, again, we can apply sort of this, come back, we could apply this acid and base definition to something that does not involve any type of H plus being transferred, and still be able to sort of identify something as a Lewis acid or a Lewis base. Later on in a later chapter, we're going to see Lewis bases a lot. A lot of times Lewis bases are involved in what we'll talk about in a later chapter, which is complex ions. So complex ions involve a lot of times Lewis bases, which donate these pair of electrons. They're sometimes called ligands in those cases. And we'll definitely see those guys again a little bit later, and maybe not so much an acid-base context, but we will sort of see them show up again. Any question about our Lewis acid bases? Again, the definition of a Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. Sort of opposite of Bronsted-Lowry in terms of accepting and donating, and then obviously Lewis and Bronsted and Lowry uses H plus is being accepted and donated, while Lewis uses electron pairs being accepted and donated. Any questions on that there? Okay. So what we're looking at here is a table, and I think we might have touched upon it earlier on in this chapter as well, but a reminder that when we do have polyprotic acids are, again, acids that have the ability to lose more than one H plus. And again, they do come off, as I think we talked about, in a stepwise fashion. So for example, if we take our H3PO4, the first thing that's going to happen is it's going to lose one H plus, and again it will basically drop off that H plus, and we'll end up with H2PO4 minus. And again, there is a Ka value for this, as we can see in this table. The next thing that will happen would be H2PO4 minus. We'll drop off that second H plus, and then we'll get to HPO4 2 minus, also a Ka value that happens with that. And the last step is this guy will drop off 2 minus that last H plus, and we'll get PO4 3 minus, which is Ka3 in this case. And that's what we see in these tables. So here's our H3PO4 and our 3 Ka values, one for each of these, as it does occur one H plus at a time. Again, if you took all three of these reactions and you added them together, you get sometimes the reaction that people think about when they look at this is, you get your 3H pluses plus your phosphate. So as we were talking about, we're going to talk about acid and conjugate base pairs. This is really why these two guys are not pairs, because they're really not related to each other. They're way down the road from each other, as you can see here, since it does come off basically one H plus at a time. So the first Ka value is 7.5 times 10 to the minus 3. The next one is 6.2 times 10 to the minus 8. And the Ka3 is 4.8 times 10 to the minus 13. What this should tell you is it is much easier to take off that first H plus, and then it gets a little bit harder as you take off that first H plus. Again, you now have something that is negatively charged. You're trying to take off something that is positively charged. So it gets a little bit harder. And we see that when we compare the values here. It goes from 7.5 times 10 to the minus 3 to a Ka value for the second step of 6.2 times 10 to the minus 8. So it's a much, much smaller Ka2 value versus a Ka1 value. A much smaller Ka2 value means that essentially when we get equilibrium, we're pretty much on the left-hand side. And as you even go one more, trying to take off that third H plus, it gets even harder. As you can see by the value here, it gets to 4.8 times 10 to the minus 13, which means not very much happening here, really mainly still staying on this side when we reach equilibrium. So this pattern happens for each of them. Here's carbonic acid, again, times 10 to the minus 7 for the first H that comes off. The second one, much, much harder, 10 to the minus 11. So it gets progressively harder to remove more H plus as soon as you take off that first one. Here's sulfuric acid, as we talked about a little bit earlier. It is a strong acid. And again, for that first value, you won't see a value in most tables. So let's write something like large. But it will be in a lot of tables because really that second part of it, that HSO4 minus, is essentially a weak acid. So there'll typically be that Ka value for that second one that comes off, although we do sort of consider it a strong acid, obviously. But there's truly not a K value that you typically will see. Obviously, large doesn't help you very much if you wanted to do some type of calculation. So when we do calculations that involve polyprotic acids, it does work similarly. But there's a few things that you have to deal with. So let's take a look at a calculation involving a polyprotic acid. And as I mentioned before, we'll get there in just a second here. Oops. Come back. Again, it does come apart in a step-by-step manner, as we talked about and saw in that table. Here we will see that the Ka value is usually much larger than the second one and larger than the third one as well. So we'll come back to that in just a sec. But let's take a look at a problem that involves polyprotic acids. So here we want to calculate the concentration of H3PO4, H2PO4 minus, pretty much everybody, PO4 3 minus. We want also the H plus concentration, and we want the pH of the solution. That is a 5 molar solution of H3PO4. Just get some numbers here. So let's take a look at what's happening here in this problem. Essentially, we want to find everybody that's happening. So here, again, these Ka1, Ka2, Ka3, they are related to those three equations that I wrote on the other slide. But again, we'll see each of them. This is basically for the first H plus that comes off. This is for the second H plus that comes off. And again, this is for the third H plus that comes off. And again, as you can see, as we saw on that table, it gets much, much smaller as we continue down. So let's take a look at a calculation here just to kind of see how it works. Maybe. All right. So we're starting with 5 molar phosphoric acid. And we basically want to find everything. So we want to find the concentration of H plus. We want to find the concentration of H3PO4 at equilibrium, the concentration of H2PO4 minus, concentration of HPO4 2 minus, concentration of PO4 3 minus. We would also like the pH, and I think that's everybody, if I'm not mistaken. So when we do a problem like this, the first thing that's going to happen is the first step. So we're going to take our H3PO4. We're going to do an ice table since it is a weak acid and we have Ka values. But again, remember, it's going to break apart one at a time. So the very first ice table will basically contain these guys here. And again, this is going to be our Ka1 value, which as we saw previously, was our 7.5 to the minus 3. So we'll do our ice table. Again, we have 5 molar here. We have 0 and 0. Our change will be minus X, and plus X, just like normal. When we reach equilibrium, we'll have 5 minus X, X, and X. I sort of missed that. We'll move it over. X, there we go. Just like normal, this would go into our Ka1 expression, which is our products over our reactants. And again, that's going to equal our Ka1 value. So put in our numbers in, we will get X squared on top. We'll have 5 minus X on the bottom. And that's going to equal 7.5 times 10 to the minus 3. I'm going to give it a go and make an assumption. We're going to assume that X is equal to 0. Again, it's our small k value, so we could give it a shot here. That gives us X squared over 5 equals 7.5 times 10 to the minus 3. We're going to multiply the 5 to the other side. We're also going to take the square root of it all in one move. And if we do that, it looks like we get a, come here, we get an X value of 1.94 times 10 to the minus 1. And again, we do want to check it. So we're going to divide it by 5 and times it by 100. And we get 3.8% or 3.9%. So the check is good here. Check is good. Thank goodness. Right. So again, we would divide that by 5 and times it by 100 to check it. So since it's good, this gives us a number of information if we go back to our ice table and kind of fill in. So if we go to our ice table and fill in our values, at this point, we see that the H plus concentration would equal X, which means we have an H plus concentration 1.94 times 10 to the minus 1 molar. We also see that the H2PO4 minus concentration also equals X, which also would equal 1.94 times 10 to the minus 1 molar. And our H3PO4 concentration is 5 minus our X, which would be 5 minus 1.94 to the minus 1, gives us 4.81 molar. Get there. 4.81 molar. So from our very first table, we were able to get this concentration at equilibrium. We were able to get that concentration at equilibrium. And we were able to get this concentration at equilibrium. So that's not too bad. But we do need to continue on because in this case, there's still more stuff that we kind of need to find here. So just kind of do it here, perhaps. So we would want to go to the next dissociation, which would be our H2PO4 minus is going to give off an H plus, and that will leave us HPO4 2 minus. Again, this is going to be our Ka2 value, which from that table and the problem looks like it is 6.2 to the minus 8. So initially here, when we come to our ice table, we do have this value, and this value comes from here, right? So it comes from above. So this would be our equilibrium value. That will be our initial value down here. So from above, we saw we had 1.94 times 10 to the minus 1. In addition, we also have an H plus concentration at this point from the above. So this is not going to be 0 in this case. This will also be what we have above, 1.94 times 10 to the minus 1, and this will be 0. So because this is sort of a continuation sort of calculation, we have already generated both of those things from the first step in the equilibrium. So we won't have zeros all the way across on the right-hand side. We will have some numbers. The rest of it's going to be kind of the same. We're going to do minus x, and plus x, which means when we get to equilibrium, we will have 1.94 times 10 to the minus 1 minus x. This will be 1.94 times 10 to the minus 1 plus x, and this would be x. Any questions on the second ice table? So again, essentially we're using the equilibrium concentrations from our first table as the initial concentrations in our second table, again, because we've already generated those guys, so it's not going to be 0. Just like above, we'll go into our Ka2 expression, and just like above, it's going to be our products over our reactants. And that's going to equal our 6.2 times 10 to the minus 8, putting our numbers in. This gives us on top 1.94 times 10 to the minus 1 plus x times x divided by 1.94 times 10 to the minus 1 minus x on the bottom equals our 6.2 times 10 to the minus 8. Since the assumption worked good the first time, that's why I picked the number that's there. We're going to assume that x is equal to 0 here. So in this case, again, it's going to be the x's we're going to plus. It's going to be the x's we're going to minus. And when we do that, that will give us 1.94 times 10 to the minus 1 times x divided by 1.94 times 10 to the minus 1 equals 6.2 times 10 to the minus 8. I think I could do that math. That gives me x is equal to 6.2 times 10 to the minus 8. Again, here we do want to check it. So we would take that 6.2 times 10 to the minus 8, and we would divide it by 1.94 to the minus 1, times it by 100, and you're like at 0.00003%. So the check is good. I won't write it up here, so I'm running out a little bit of room here. So the check is good, but you should check it. So what does that mean? That means that from our table, if we go back to our table at equilibrium here, we now have been able to get the concentration of HPO42 minus, which equals X. That means it equals 6.2 times 10 to the minus 8 molar in this case. So from this table, we're now able to get the concentration of this guy. Now, what happens when I put this number here, 6.2 times 10 to the minus 8, back into both of these locations here? And if we do that, and if you do that, and you put it back into each of those numbers there, and you take 1.94 times 10 to the minus 1 plus 6.2 times 10 to the minus 8, you will still get these numbers. It will still be the same, basically. So the concentration there of the H plus and the H2PO4 minus did not really change from its initial concentration here at equilibrium very much. And that, again, is because of the very small K value that we got going on here for that second H plus to come off. Any questions on that there? So again, come back. So again, the concentrations of H plus at this point and H2PO4 minus pretty much are remaining constant, hasn't changed all that much. Technically, it's changed by 6.2 times 10 to the minus 8. That's a very, very small amount. So when we look at what else we're trying to find, we still are looking for our PO43 minus. So that is, in this problem, going to require us to do the very last dissociation, which is that last H plus is going to come off. And I'm going to do that obviously on the next page because I'm a little bit out of room here. So the next thing that's going to happen again is our last H plus is going to come off. And again, this is our Ka3 that's happening at this point, which was 4.8 to the minus 13. Again, when we go to do our ice table, if we back it up, we again will have a starting concentration. That's our equilibrium concentration from the previous table. So that's our 6.2 times 10 to the minus 8. And we will still have the same H plus concentration because, again, this has not really changed as well. So just like this table here, we will have an initial concentration of those guys from the previous table. So coming back over here, our initial is our 6.2 times 10 to the minus 8 from the previous table. Again, the getting old 1.94 times 10 to the minus 1 from our previous table as well, the equilibrium. So here we will have 0, though, for our phosphate. Our change is going to be minus X, plus X, and plus X on that side. Going to give us at equilibrium 6.2 times 10 to the minus 8. Minus X, 1.94 times 10 to the minus 1 plus X, and X going into our Ka3 expression, our products, and divided by our reactants. Going to equal our Ka3 value, which we can see is very small. And we get on top 1.94 times 10 to the minus 1 plus x times x divided by 6.2 times 10 to the minus 8 minus x equaling 4.8 times 10 to the minus 13. Why not make the assumption we've been good all day here? X is equal to 0. That's going to give us up on top 1.94 times 10 to the minus 1. Going to give us times x divided by 6.2 times 10 to the minus 8 equals 4.8 times 10 to the minus 13. I'm going to multiply the bottom to the other side and divide by what's on top there, the 1.94. So 4.8 to the minus 13 times 6.2 to the minus 8 divided by 1.94 to the minus 1 gives us an x value of 1.53 times 10 to the minus 19. Again, we want to check it. We can divide it by either number. So we'll divide it by the 1.4 times 10 to the minus 1 times 100. And again, I think we should be good. And you're nowhere near 100, nowhere near 5% or even 1%. Check is good here. So what does that mean? That is going to be our x value here. So again, if we go back up to our equilibrium line and we plug that number in, we see that the concentration of PO4 3 minus equals x in this case, which is equal to 1.53 times 10 to the minus 19 molar, which again, kind of checking back, is the one of the last things that we're looking to find here, our PO4 3 minus. Same deal as what we had last time. When you put this x value back into here and back into here, because it is so small, these numbers still do not change, and they basically remain the same. And what that means is, as you could see, we had H plus in all three steps. Had H plus here, which essentially remained the same because it didn't change. We had H plus in our second one, which also remained the same number because this number was very small, so it didn't change. Which means essentially what we see and what happens typically with most polyprotic acids, we see that the only place really where the H plus concentration changed the most was here at the first step, which it also was the exact same concentration as it was through step number 2 and step number 3. And that is because of what we were talking about, that it is much harder to remove that H plus after you remove the first one. And then it gets even harder, as you can see in this example, to remove that third H plus. Not very much is happening. So if you look at the second table here, the change was 6.2 times 10 to the minus 8. That is an extremely small amount of change that's happening. Not very much at all is coming off in terms of H plus, and even less, as you see when we get to our last step to the minus 19, even less H plus is coming off in that case. So what typically happens if you are asked, like in this problem, for example, to calculate the pH of this solution, it is usually pretty safe to calculate the pH from the first H plus concentration, as that is the majority of H plus that's going to come off. So that means to calculate the pH, which is the last thing we're looking for, minus the log of the H plus concentration, we would take minus the log of the H plus, which again, pretty much did not change throughout the entire 3 steps. And that would give us a pH for the solution of 1.94 to the minus 1. and that's like a 0.71 pH in this particular case. So if you have a question that involves a diprotic acid, a polyprotic acid, triprotic acid, and you're really only asked to calculate the pH of that solution, pretty much you will be safe if you just take the first H plus concentration, because not very much is going to usually come off in most cases. And the second step, or even the third step, if you're talking about a triprotic acid. Now, in this particular problem, because of what was asked in this problem was everybody up here on top. We wanted the concentration of everybody, including PO4 minus, HPO4 minus, all these guys. That really is, in this problem, the only reason why we had to go through all three steps, because the only way to get to, for example, our PO4 minus was to go through each of the steps of the H pluses coming off. So if you're asked a question like this, where you have to kind of find the concentrations of everybody at equilibrium, it may require you to go through each of these steps in a stepwise fashion and do an ice table for each of them. But again, if you're asked just sort of a more basic question of what is the pH of that solution, you pretty much could just do the first ice table, get the H plus concentration, and go into the pH, and you probably will be okay in terms of the answer. Any questions on how to deal with a polyprotic acid and calculating pH and so forth? Okay. So the next topics we're going to talk about here are really buffers and common ions. So let's get into that maybe. And this again is the part of the class where a lot of people, find some difficulties with what we're talking about coming up here for the rest of this chapter. We're going to talk about buffers and titrations. Those are the big two sort of topics. These are the topics that you do need to fundamentally understand what is happening so that you could do the correct math. Because again, there'll be a lot of places in these problems where you could do all this wonderful math, but it's all completely wrong, because that's essentially not what's taking place in this problem. So it's very important that you sort of understand the conceptual aspect of sort of what's happening here. So when we talk about a common ion, or the common ion effect, the common ion, much like the name implies, is a situation where you have a solution, a weak electrolyte, like a weak acid, for example, or even a weak base, where in that solution, it will set up an equilibrium. So for example, we have acetic acid there on the bottom. It's right up here. And when we have something like acetic acid, again, is a weak acid, which means when it's in solution, it will set up this equilibrium of H plus and acetate. Now, if we just had acetic acid sort of by itself, it will naturally, obviously, come to equilibrium here, just like what we see on the screen. But if we decided to add to the solution a strong electrolyte, something like sodium acetate, which is what it shows on the bottom there. So this sodium acetate is a salt and a strong electrolyte, which means it's going to 100% break apart into sodium ions in solution and acetate ions in solution, right? So unlike our weak acid over here, it's not going to set up an equilibrium in solution. This is what you're going to have, 100%. You're going to have these ions floating around. Now, what it means by the presence of a common ion will suppress the ionization of a weak acid or weak base is just this. The ion that's in common here is our acetate ion. And by adding sodium acetate to the solution, it's effectively adding more acetate to it. And when we add more acetate to it, our good friend Le Chatelier, right, will tell us, hopefully you know this, in about an hour, right, that when we add more, excuse me, acetate, it's going to cause a shift in the equilibrium. I'll use a giant arrow. I don't know why. Just feel like it today. It's going to cause the equilibrium to shift to the left. And when it causes the equilibrium to shift to the left, that means what we will have is more of our intact acetic acid. Yeah. And ionization or dissociation is when these acids break apart into their ions. So by adding this common ion, it's going to cause that shift to the left-hand side. And what it's going to essentially do is keep that acid basically together. And when it keeps it together, that means that we will have, in terms of free H plus, like on the right-hand side here, free H plus, we will actually have less free H plus. Yeah? And that's important in terms of pH, because if we have less H plus, we would expect the pH to start moving upwards, right? Less H plus means more OH minus. Not necessarily will it become basic, for example, but the pH will move up from where the acetic acid pH would be by itself. So where the acetic acid pH would start, let's just say it started at like a pH of 2-ish. If we add something like sodium acetate to it, it would move upwards. And that solution that has both the acetic acid and the sodium acetate in it would perhaps have a pH of not like 2, but maybe in the 4-ish sort of range. So it would move up. Again, not necessarily mean all the way up to like basic area or anything like that, but it would move upwards from the weak acid by itself. So it would definitely move higher in terms of the pH, but like I said, not necessarily basic. Any questions on that? Very commonly thought about by people, or maybe not sure what happens. The sodium there, really just a spectator ion, just kind of hanging out to balance out charges, not really participating, in anything. So let's take a look at these couple of examples and sort of see the difference between what we end up with. So let's take a look first at the first one here, which is where you have acetic acid, which the Ka value is 1.8 times 10 to the minus 5. And we're going to start with 0.2 molar of it. All right, so let's take a look at that one first. So this one really is just a Ka type problem, part A. And in part A, we have 0.2 molar acetic acid with a Ka value of 1.8 times 10 to the minus 5. And we're interested in what the pH is. So again, to do this, just a basic Ka problem, we have our weak acid that's going to drop off that H plus. Initially, just like a normal one that we've done a lot at this point, 0.2, 0, and 0. Our change is going to be minus x, plus x, and plus x, which means when we do get to equilibrium here, we're going to have 0.2 minus x, x, and x. This is obviously going to go into our Ka expression, so that's going to give us x squared over 0.2 minus x equals our Ka value for this, which is 1.8 times 10 to the minus 5. Since I've been having some luck today, we'll continue our assumption. Watch, my luck will run out here. We're going to assume that x is equal to 0. So that's going to give us x squared over 0.2 equals 1.8 times 10 to the minus 5. We're going to multiply the 0.2 to the other side. Also going to take a square root, so I don't forget that part. And it looks like we'll call it x is equal to 1.9 times 10 to the minus 3 in this case. We do want to check it, so we're going to divide it by 0.2 and times it by 100, and I believe we're at 0.9%. So this check is good. So we're all good. We can use that as our H plus concentration. So again, I won't show the check, but we do the same thing. Check is good. Again, divide it by 0.2, times it by 100. And again, you're at like 0.9%. So really for pH, it is the H plus concentration, which is an importance here. That equals X from our table, as you can see right there. And that means that that equals 1.9 times 10 to the minus 3. That means that the pH here would be minus the log of 1.9 times 10 to the minus 3. And that's going to give us an opening pH here of 2.72, which is good because that is acidic. And we are dealing with an acid, right? So our pH is 2.72 for part A. Any questions on those steps? Those are essentially the exact same steps that we did, obviously, at the beginning of this chapter here. Just a basic sort of Ka problem. And we did get, obviously, an acidic pH. Any questions on where any numbers came from or, how I got any of those numbers? Okay. So, and again, if you do have questions, feel free to type them. I will definitely answer them. We're going to look at part B now and see how it's slightly different. Now, in part B, we have a solution that contains 0.2 molar acetic acid. And it also contains, that was 0.3 molar, I believe, 0.3 molar sodium acetate. And we also want to know what the pH of this solution is. And the Ka value for our acetic acid was given to us, which again is our 1.8 times 10 to the minus 5. So the important thing to recognize is we do have a mixture of a couple of things here. This is our weak acid, which again, just like above, will set up an equilibrium in solution. This sodium acetate, as we saw on the previous sort of slide, is not a weak acid. It's actually a strong electrolyte. And again, in solution, it is going to 100% break apart into those ions that we saw previously, the sodium ion plus the acetate ion. So again, just to be clear, this guy will not set up an equilibrium because it's a strong electrolyte. So in solution, really the only guy that is setting up an equilibrium is our acetic acid. And it would be the exact same equilibrium or reaction that we had above. Now, initially we had, just like above, 0.2 molar. We still have 0 of this guy initially, but because unlike in this solution, where all you have technically kind of floating around is, your acetic acid, your acetate, and your sodium, right? Actually, no sodium in this guy. You have the same situation here, but you kind of artificially, again, added more acetate to it. So we will not have a 0 here for this guy. We will actually have a number, and the number would be supplied by the sodium acetate. So since the sodium acetate is 0.3 molar, it's a 1-to-1 relationship between the sodium acetate and the acetate. The concentration of the acetate part will also be 0.3 molar, as again, it's a 1-to-1 relationship. So where people always screw up on this table, if they do the table, is right there. This should not be 0 in this case. If you did 0, you're doing this problem again, which is not what's happening. So it's really important, especially when you have that common ion, that on the left-hand side and the right-hand side there, where you have the common ion and you do the ice table, it definitely should have a number associated there. Now, the rest of the table is pretty much the same. This could be minus X. This is going to be plus X. This will be plus X. This means that when we get to equilibrium here, we have 0.2 minus x, 0.3 plus x. Any questions on the table and how it's different? So again, just to review, it is just the weak acid that's going to be able to set up that equilibrium. Again, the sodium acetate is a strong electrolyte, which means in solution it's just going to produce ions. Those ions are going to be our common ion in this case, which is the acetate. And what that essentially means for our table is initially we have some acetate involved and should not be zero. The rest of it is going to be the same. So we're going to go into our Ka expression. That's going to give us x times 0.3 plus x divided by 0.2 minus x equals 1.8 times 10 to the minus 5. Minus will go with my nice assumption there. X is equal to 0. Going to give us x times 0.3 divided by 0.2 equals 1.8 times 10 to the minus 5. Again, we're going to multiply the bottom to the other side and divide by 0.3. So 0.2 times 1.8 to the minus 5 divided by 0.3 gives us 1.2 times 10 to the minus 5, I believe. Just double checking and hit the wrong button there. Yeah. So that is 1.2 times 10 to the minus 5. Again, we want to check it, so we could divide it by 0.2 times it by 100. And again, if we do that, I think we should be good. Again, not even 0.1%, so this is good. Check is good. So that means, again, in terms of pH, it really is the H plus that we're interested in. So our H plus concentration will equal X in this case, which equals 1.2 times 10 to the minus 5. That means our pH would equal minus the log of 1.25 times 10 to the minus 5. And that's going to give us a pH for this guy of 4. Sorry, I put an extra 5 in there. My bad. Sorry. Added it for free, I guess. Minus the log of 1.2 to the minus 5 gives us a pH of 4.92. For this solution here, that was the one that contained the common ion. Any questions on that? We also see that the presence of the common ion suppressed the dissociation of that weak acid. So in part A, no common ion, we had a pH of 2.72. With the common ion present here, which caused ultimately a shift in the equilibrium to the left based on Le Chatelier's principle, made sure that we had actually less H plus present. And as you can see here, as we were talking about, what we see is the pH actually went up when compared to the weak acid by itself. And that is typically what you'll see here. Again, if you did this calculation for the second part and you got a pH that's less than what you started with up there on top, definitely something went wrong in the calculation. Any questions on any of those parts there? Now, in this particular problem, and in problems that basically involve common ions, what we usually see is the concentration of our H plus and acid and everybody at equilibrium. The change is not that much. So the concentrations of our acid and base that we start with is essentially the same concentrations as what we end with. And if you look back on this table right here that we just did, wherever it went, there it is. Essentially, if I took 0.3 and I added 1.2 to the minus 5 to it, it's essentially going to remain at 0.3. Same thing over here. If I took that 1.2 times 10 to the minus 5 and subtracted it from 0.2, it will essentially remain 0.2. So essentially what happens when we do have these common ions is our initial concentrations actually end up being our sort of final concentrations for each of these things. And in a situation like that, you can consider the starting concentrations your equilibrium concentrations for your weak acid and really its conjugate base, because that's essentially what we have here, right? This is basically our weak acid and this is its conjugate base, right? So those are the relationships between those. So when you have a problem that involves that, you could think of the initial concentrations as the equilibrium concentrations. And what that will allow you to do is, in certain cases, not necessarily has to do an ice table. You could use everybody's favorite, the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation is this equation right here in the box. This is how we get to those equations. But really the ones in the boxes are the important one here. It is the pH is equal to the pKa value plus the log of the concentration of the base over acid, essentially. And how we calculate the pKa value is the pKa value is equal to, as we see down there, minus the log of the Ka value. So what that means is if you have a common ion effect, which as we'll talk about in just a second, really is a buffer. And this is really the equation that goes with a buffer. If you could recognize it as a buffer or really a common ion effect, you can basically go right into the Henderson-Hasselbalch equation and you would not have to do an ice table at all. You will get the actual same answer. So for example, let's take a look at the one that we just did. And the one that we just did was we had 0.2 molar acetic acid with 0.3 molar sodium acetate. And again, the Ka value was 1.8 times 10 to the minus 5. When you look at these two things, again, you should be able to recognize this hopefully as a weak acid because of the Ka value. And again, if you get rid of the sodium here, you have acetate, and that would be its conjugate base. Yeah? So that's really the ultimately what a buffer is. And we have a weak acid and its conjugate base, or you can have a weak base and its conjugate acid. And if you can recognize that, you actually can go right into this equation without doing an ice table with our Henderson-Hasselbalch equation. And we do need to calculate the pKa value. So the pKa value is minus the log of the Ka. If I stop hitting the wrong button, gives you minus the log of 1.8 times 10 to the minus 5. That's going to give you a pKa value of 4.74 when you do it. And now we can go into our expression here. That will give us 4.74 plus the log of our base, which again is his guy. So we want the 0.3 on top. We want our acid on the bottom. And if we do all that good math there, we get the exact same answer of 4.92 as we did when we did it on the bottom way. So what I just did and part B calculation that we just did is the exact same thing. So you can see it's a little bit quicker probably than going through the ice table and assuming and checking your assumption and stuff like that. So you could definitely for part B here use the Henderson-Hasselbalch equation. You cannot for part A because you don't have the conjugate base. Yeah, so you only have the conjugate acid or the weak acid given to you, no conjugate base. But in part B here, which is the same one I just did over here on the next slide, you can go into the Henderson-Hasselbalch equation. So this gives you another way to calculate the pH of a solution that involves a weak acid and conjugate base, or even a weak base and conjugate acid situation, you can use the Henderson-Hasselbalch equation. If you don't want to use the Henderson-Hasselbalch equation, what that calculation in part B that we did previously shows you, you could still do an ice table. Again, if you choose to do the ice table, you want to make sure that you have that initial concentration on the product side of your common ion, which is very commonly, again, where people screw up if they decide to do the ice table rather than the Henderson-Hasselbalch equation. They always mess up on that initial part of the table. So you want to make sure that you get that correctly. Now, you should not, just to be very clear, the Henderson-Hasselbalch equation is really specifically only for, as we'll talk about here, buffers, yeah, which is our common ion. So if you do not have a common ion effect or really a buffer, you should not use the Henderson-Hasselbalch equation. That is also where people screw up in this chapter, is they decide, I'm just going to do it everywhere. Anywhere I got two numbers, I'm just going to throw it in there. Remember that in order to put it in for the base of the acid, they do need to be related to each other as a weak acid and a conjugate base. Any questions on that there? So if we look at this one, why don't you take a minute there and give it a go and see what you come up with. Calculate the pH of this solution. Okay, so let's take a look here. So in this case, we have, excuse me, we have 0.3 molar formic acid. We're also mixing it with 0.52 molar potassium formate. And we have a Ka value, which would go with our acid, which is this guy. So we should hopefully be able to recognize that as an acid. This guy is lacking the extra H plus. This has a metal like a potassium, a sodium, a lithium. You know, that's how you could kind of tell that these guys are really more of a salt, right? Which is uh, a strong electrolyte. So in solution, this guy here is going to 100% break apart into our formate and our potassium, right? And it is this acid part here that would technically set up the equilibrium. And it would look something like this. And again, it would be this guy that would be our common ion here. And since we do know that this is 0.52 molar, it's a one-to-one relationship. This would also be 0.52 molar. If you chose to do this through the ice table, your ice table should kind of look something like this. Again, because this is a common ion, we should have an initial concentration here, minus X, plus X, plus X. And if you went to equilibrium there, 0.3 minus X, X, 0.52 plus X. Now, this is what your table should look like. Obviously, you continue on to your Ka, to your X, to your H plus, and then to your pH. And you can do it that way perfectly fine. But again, if you could recognize that these two things are related to each other, again, essentially what we have is a weak acid and again is conjugate base, which as we'll talk about later in this chapter here in just a sec, it's essentially a buffer and a common ion. So you could go actually directly into the Henderson-Hasselbalch equation without doing the ice table. You do need to get the pKa value, which would be minus the log of the Ka, which is 1.7 times 10 to the minus 4. That's going to be a, don't change the page, going to be a 3.77, I believe. And that would get us that the pH is equal to 3.77 plus the log. Again, this is our acid. It's got the extra H. This is our base. It's missing an H is a good way to remember that. So the base should go on top and the acid should go on the bottom there. And I believe we will end up with 4.01 in terms of our pH value. Again, if you go this route, you should also end up with 4.01 with rounding and stuff like that. It should be pretty close. So again, you do have two ways to do it. You could kind of see if you recognize it as a really a common ion or buffer type problem, probably going in that direction into the Henderson-Hasselbalch is probably the easier of the two. And that obviously will give you the answer quicker. But again, if you're not sure or can't remember the Henderson-Hasselbalch equation for some reason, you could always fall back to the ice table and do the ice table. But again, in these common ion or really buffer problems, this is the super important part where people screw up. You gotta have an initial concentration for your conjugate base, or if you're doing a base, your conjugate acid on that side. So if it's common ion, you should have for that initial a number on both sides in order to do it correctly. Any questions on that? All right, so this is a good stopping place. So we'll stop here. Let's talk about a couple of things that's going on. First off, in about a half hour at 11:30, the exam will be open for you to take. You'll have a window of time, I think, until 3:30 to submit it. So just like the quiz, The 3:30 cutoff is the last chance that you'll have to actually submit the exam, not start it. So again, if you start the exam like at 3:20, it's only going to give you 10 minutes to take the exam. So if you started around 11:30 or normal lab time, you should have all the time that you will get on the exam. You will get 150 minutes, which I think is 2.5 hours. So that should hopefully be enough time for you to take it. Make sure that you start the exam with at least 150 minutes before the cutoff time. Again, if you do not, then you will be cut off exactly at whatever it is. I think it's 3:30 and so forth. So it gives you a little bit of leadway in terms of you don't have to start exactly at 11:30, but don't wait too long. Otherwise, again, it will cut you off and you won't get that time. Just like the quiz, you'll be able to see all the questions at once. They're all up there, so you can work on any question you like, sort of in any order and stuff like that. Just like last time, do not hit the submit button until you have 100% completely answered all the questions that you plan on answering. Again, it will give you a warning sign if you do that and if you haven't answered questions. That hopefully should tell you not to do it. But if you submit it early without answering all the questions, it will not be reopened for you. So it will not be reopened. There will be a lot of work to show, obviously, for our sort of testers, work to show with it. So just like on the quiz, you need to have some paper, obviously a calculator, and you need to show the work. That includes all the setup, the units, and all the correct answers. Each question, much like the quiz, is labeled as you need to show work or you don't need to show work. Unfortunately, I think a majority of them you do need to show work. There's a couple I think that you don't need to. Um, there's also specific instructions on each of the questions as to how to answer them, like give the answer to 2 significant figures, give the answer to 1 decimal place. Make sure that you do follow the instructions on each of the problems when you submit an answer online. Um, Also remember that if it is a numerical answer, do not include units online, but do include the units and everything um, in your work that you show and upload. Okay. Now, if you enter a number, for example, say in scientific notation, or you enter a number into Canvas and it lops off the last zero or anything like that, it's okay. So just let it be on your paper. Make sure that you show it to the correct numbers that it asks you to do so, because it will sometimes maybe change your number from scientific notation into like a decimal sort of number or a whole number without scientific notation. And in certain cases, it may lop off like the zero or something, and it's okay. So you don't have to worry about it. It'll all be okay in the end. Just make sure you show it correctly on your work. Um, you'll have a periodic table there, which honestly, I don't even know you need the periodic table, but it might make you feel good to have it, I suppose. Really, the only conversions that you need, I think, are the R values, and those are given to you. I don't think there's any other conversions. So there's conversions up on the top when you start the exam. There's also the periodic table there, and again, each of the questions. Remember that you do need to submit an answer for every question online in order for your work to be looked at. If you do not submit an answer online, I will not look at your work. You can't just say I did everything on the paper. So you do have to make sure that you both submit an answer online, and obviously the work should basically complement that answer that you submitted online. It should be basically the same. Any questions on the exam? So again, you have 150 minutes. Again, make sure you start somewhere around the 11:30ish area to like 12. You should be okay. You won't run out of time, but don't start too late or anything like that. When you're done with the exam, just like the quiz, you'll have to go in order. So you'll have to do the academic honesty agreement. You'll have to sign it. It'll then let you take the exam. Once you've submitted your exam on the module section where it is, it will open up the assignment where you can upload your work for the exam. Okay. Now, for the textbook homework, there is a separate module for that to upload your textbook homework. So please upload that in the correct one. It's a separate sort of spot on in the module section for that. Okay. So you have 2 things to upload, really: your work for the exam, which goes in the assignment that's in the module for the exam. And then separate from that is your textbook homework, which goes in on a separate module. It'll say textbook homework upload. So make sure that you put those guys in the right spots as well. Once you submit your exam, you're expected to submit your work in a timely fashion. After you submit it, Make sure you upload it in timely fashion, not hours later or anything like that. So make sure it's all done within a timely fashion. Yeah, for the homework, however, whatever is easiest for you to do it. If you want to put it all in one file, you can. If you want to do it one file for each chapter, you can do that. Just as long as I have it. More importantly, just make sure that you upload the homework in the right sort of assignment. So make sure it's the one that says textbook homework. So make sure that gets uploaded, in the right one. So I don't have everything in all different places, everything together. So make sure that that textbook homework is uploaded. And again, however you want to do it, one file, two files, it doesn't really matter to me, just as long as it's uploaded in the right spot. Other questions about the exam or anything like that? So we will not have obviously lecture day. We wish we did, but we will not have lab today. Obviously, you'll be using that time obviously to take the exam. The other thing that you might have saw on Canvas is I have uploaded now the pH and hydrolysis experiment, which is technically the one we were starting last week, this week, kind of thing. So it's up there for you to work through. You should be able to work through it. I did make some changes. Originally, it was supposed to have sodium bicarbonate for part two. It has been changed to sodium cyanide. And I think I changed it on everything. But if you still see somewhere sodium bicarb for part two of that experiment, just change it to sodium cyanide. That's going to be due, I think, towards the end of next week. So that will be due towards the end of next week. So if you're done with the exam or tomorrow or whenever, if you want to start working on that, start working on it, and you should be able to work through it. The lab report for that will be yeah. So I think honestly, we're going to take a little sort of break. So we're going to work on this week the pH and hydrolysis lab. I think truthfully on Thursday we're going to do some lecturing. Uh, we may do some lecturing in the lab to see where we're at, just to try to keep on pace with everything. So right now, since we haven't talked about buffers yet, we're not going to obviously start buffers on Thursday. So right now, just concentrate on the pH and hydrolysis one that you can start working on this week. Tomorrow, it's already up there. So you can actually start working on it. And then maybe during Thursday lab, if you have questions on it, you could ask questions on that. And we may do some lecturing on Thursday lab as well, just to kind of keep on pace and everything. So we'll probably officially kind of start the buffer lab probably next week on Tuesday is probably where we'll officially start that one. Other questions on that? So again, like I said, the pH lab is up there, so you can start working on it. And the lab report for that will be pretty much what it says. It just has different data pages and stuff to fill out. So there will be no typed lab report for that one or anything like that. It's just sort of your kind of fill out the pages and your observations and calculations. So you'll kind of see it as you go through the module. There'll be different sort of things to fill out and upload, and that would be basically the report for that one that's coming up. Any questions on anything else? So again, during the exam, I think everything should be pretty self-explanatory. If for some reason you do have questions, I will be checking my email. So you could email me through Canvas if you need to do that. If at any time, again, a reminder, once you start the exam, the timer will not stop. So make sure you're completely ready to take the exam before you begin. Even if you click away, the timer will continue to tick. So make sure you're ready to start it. If you do kind of click away and you need to find it again, go back to the module section. You'll be able to click back through and into it. But if you do have any type of questions, you can email me. I'll try to answer them. Remember, I can only answer sort of unclear things. Can't tell you how to do something, but I think everything should be pretty self-explanatory. It's going to be very much like the quiz that we took. Also, a friendly reminder, there are different versions of the exam. So obviously you should only use the stuff that is provided for you. You should not use any outside aids, the internet, or anything like that when you're taking the exam. Obviously, it should be you taking the exam and all that kind of stuff. So just a reminder, there are still different versions. So don't have the right answer on the wrong version. That will not be good. Yes. All right. Any other questions before we wrap this up and give you a little break? Again, nothing is going to be available yet until about 11:30. Right at 11:30, you'll probably get like an announcement email that says it's open and ready to take it. And then obviously make sure you're prepared to take it before you begin. And obviously, like I said, you get 150 minutes, which is I think 2.5 hours. That seems like a lot of time. That should be hopefully plenty, I hope. And make sure that you do start 150 minutes before that cutoff time. That way you won't be cut off too early. And make sure you only submit it once. Any other questions on anything? And like I said, if you're looking for something to do, obviously you can start the pH and hydrolysis experiment, which we obviously have talked about everything in there. So you should be able to do that. And I believe you also have perhaps the equilibrium experiment due coming up this week, I think. So make sure you finish that as well. All right, good luck on your exam. I'll see you again on Thursday live for our lecture. And until then, have a good rest of your day.